Welcome to Engineering, Measurement, and Control Systems. I'm Mr. Akawa, and today we embark on a comprehensive journey, starting with Chapter 1, Measurement, Classification, and Methods. Measurement is the quantitative assignment of values. We classify measurements as direct, where the quantity is compared directly to a standard, or indirect, where the quantity is determined from other measurements using a known relationship. Consider static measurements for quantities that don't change rapidly versus dynamic measurements for those that do. Methods include physical contact or non-contact techniques, and the output can be analog or digital. A generalized measurement system comprises a primary sensing element, a transducer, signal conditioning, a display, and sometimes a feedback system for control. For instance, knowing if a liquid's temperature is right often relies on indirect measurement. Now, a quick check. Which of the following is an example of an indirect measurement? A measuring length with a ruler, B, measuring weight with a scale, C, measuring temperature with a thermometer, D, measuring current with an ammeter. The answer is C. Chapter 2 delves into signal processing and conditioning instruments. Signals from sensors are rarely perfect. They require processing to be accurate and useful. Signal conditioning involves processes like amplification to boost signal strength, filtering to remove unwanted noise or specific frequency components, attenuation to reduce signal strength, and crucially, analog to digital conversion, transforming continuous signals into digital data for computers. We also use isolation for protection and noise reduction. Common instruments include the oscilloscope for waveform visualization, the spectrum analyzer for frequency analysis, multimeters for basic electrical measurements, and data acquisition systems for comprehensive data collection. Let's test your understanding. What is the primary purpose of a low-pass filter? A 2-block low frequencies. B, to allow high frequencies to pass. 100 to allow low frequencies to pass. D, to amplify all frequencies. The correct answer is C. Finally, Chapter 3 explores the principles of control system technology. A control system regulates the behavior of another system. We distinguish between open-loop systems, which operate without feedback, like a simple toaster where you set a time regardless of how toasted it gets, and closed-loop systems, which use feedback to adjust their output and achieve a desired state. Much like a thermostat regulating room temperature, key components of a closed-loop system include the controller, the plant, which is the system being controlled, sensors that measure the output, and actuators that execute the control action. A cornerstone in control system design is the PID controller, which combines proportional, integral, and derivative actions to achieve precise control. Proportional action responds to the current error. Integral action addresses past errors to eliminate offset. And derivative action anticipates future errors. PID controllers are widely applied in everything from industrial automation to vehicle cruise control. Time for another question. Which component in a closed-loop control system measures the output and feeds it back? A, controller. B, actuator. C, sensor. D, plant. The answer is C. This concludes our detailed overview of engineering, measurement, and control systems. We've covered classifications, signal processing, and control system fundamentals. Thank you for watching, and I look forward to our next session.